The law of conservation of energy and efficiency. In this lesson, we'll be talking about the law of conservation of energy, total mechanical energy, conservation of energy, other forms of energy, energy efficiency, and then a whole bunch of applications and practice. The law of conservation of energy. The law of conservation of energy states that for an isolated system, so a system that is contained, energy can be converted into one form or another, but it cannot be created or destroyed. So for instance, in this case here, we have chemical energy, chemical potential energy specifically inside the cannon. When that chemical potential energy releases the energy, it gives the cannonball kinetic and potential energy. When it reaches its max height, it's going to have less kinetic energy, more gravitational energy, and when it hits the ground, all that kinetic energy and potential energy is going to be converted into thermal energy, heat energy, as it hits the ground and releases its energy. So here's an example. So if you have a 50-kilogram swimmer, jumps from rest 3 meters above the water on a diving board. At the diving board, the swimmer has zero kinetic energy. So that's the diving board, and then the water below looks like that. So then here's our guy up here, and he is 3 meters from the water. So at the diving board, the diver has zero EK. Now he has zero EK because he's not moving, but he does have potential energy, and that's where his maximum potential energy is, and it's all relative to the surface below. So together, the kinetic energy and the gravitational potential energy make up the swimmer's mechanical energy, total mechanical energy. And you can see it in our table on the bottom here, at a height of 3 meters. All our energy, 1.47 times 10 to the 3, is in gravitational potential energy, while 0 is in kinetic energy. And then that 1.47 times 10 to the 3 makes up our mechanical energy. Now when the swimmer falls, so he goes from there to here, as he falls, that potential energy is converted to kinetic energy. So at this point here, we're going to have half of our total energy is going to be in EK, and half of it is going to be in EG, potential energy. And then when he hits the ground, or excuse me, hits the water, all of that potential energy is converted into kinetic energy, and he no longer has any gravitational energy. So say it's all in EK. And you can see that in our chart again. So at the bottom, when the height is 0 meters, all the potential energy is gone, and all of that energy, that 1.47 times 10 to the 3 joules, is converted into kinetic energy. And the reason for that is that the height is gone. Remember, EG, potential energy, is equal to mgh. When that h goes down to 0, then this guy, the whole potential energy, goes down to 0. Total mechanical energy. Total mechanical energy we write usually as ET, and it's the sum of the EG and the EK. So EK plus EG gives us ET. So in example 1, you can see right here on the left-hand side, let's just say that that is halfway. That might be our total half height. So in this case, half of the energy is going to be kinetic energy, and half of it is going to be potential energy, giving a total of 100 joules. And number 2, over here, we can see that most of that energy is now in EG, because we've gained height. As we gain height, we lose speed. So you can see that our EK went down, and that's represented by the 70 EG and only the 30 EK. Now number 3, almost all of that energy has been converted into EK. So you can see now we're at 90 joules EK, 10 joules EG, and that still gives us 100 joules ET. So energy isn't lost, it's not created, it's just changed from EK to EG in this situation. Now this is assuming that there's no air resistance, that there's no friction, so there's no energy lost to the system. That's all contained within the card itself. Check your understanding. As the water in a river approaches a 5.7 meter drop, its average speed is 5.1 meters per second. So let's just draw that out. So our water here is going to draw it as a bubble like that. And the height, we're told, is 5.7 meters. And the speed right here is 5.1 meters per second. For each kilogram of water in the river, determine the following. A, the kinetic energy at the top of the waterfall. EK equals 1/2 mv squared, which is equal to 1/2 times 1, because 1 kilogram, times 5.1 squared. And that equals to 13 joules. And that's 2 sig digs, that's what we need. B, the gravitational potential energy at the top of the falls relative to the bottom. So that's going to be our EG. EG is going to equal to mgh. M is 1, G is 9.8, and our height we're told is 5.7. And that equals to 56 joules. It's actually 55.86 joules, which we might need after. But the correct answer to 2 sig digs is 56 joules. C, what is the total mechanical energy at the bottom of the falls? Well, the E mechanical at the top is going to equal to the mechanical energy at the bottom. Now at the top, we'll say EM top. We know it's going to equal to the total EK plus the total EG. And you can see our numbers right there, given again. So that's 13 plus 55.86, and that equals to 68.86 joules. So what is the total mechanical energy at the bottom? Well, we just said that EM top is going to equal to EM bottom. So the total mechanical energy at the bottom is going to equal to the same as at the top, which is 68.86 joules, which we need to round to 69 joules. D, what is the speed at the bottom of the falls? Well, as the water falls, all that mechanical energy is converted into kinetic energy. Now, some of it was already kinetic energy, but all that EG is converted into EK as well. So we're going to say that EM top is going to equal to EK bottom. We know that at the top, it's 68.86 joules, and that's going to equal to 1/2. Now it's mass of 1, and then V squared. Now we're going to rearrange, solve for V. We're going to say that V is going to equal to the square root of 68.86 times 2, and that equals to 11.74 meters per second, which comes out to 12 meters per second to 2 sig digs. And remember, we're talking about energy, we're just talking about scalar quantities, therefore we're going to leave it at 12 meters per second with no direction. Check your understanding. A basketball player makes a free throw shot out of basket. The basketball leaves the player's hand at a speed of 7.2 meters per second from a height of 2.21 meters above the floor. So let's draw that in. There's the basketball. We're told that the basketball leaves the player's hand at a height of 2.21 meters, and it's going at a speed of 7.2 meters per second. Draw a picture of the scenario, which we just did, then determine the speed of the basketball as it goes through the hoop 3.05 meters above the floor. Note, the direction and therefore the sign, plus and minus, doesn't matter as energy is a scalar quantity. So now let's get this out real quick. It's going to go up like that, and it's going to go into the hoop like that. That hoop, we are told, is 3.05 meters above the ground. Okay, so now what we need to do is we need to say that ET at the start, so we'll call it ET1, is going to equal to E total 2, right? This is 1, and this is 2. Now, what makes up the energy in number 1? Well, in number 1, we're going to have kinetic energy. We're going to call it EK1, and we have EG, potential energy. We're going to call that EG2. And that's going to equal to, of course, the kinetic energy at 2 plus the gravitational energy at 2. And now we can put some numbers in. EK is going to equal to 1/2 M. Now the V is 7.2 plus mgh, mass we don't know. G we know is 9.8, and we know the initial height is 2.21. Equals EK2, that's going to be the speed as it goes to the basket, is going to be equal to 1/2 M, we don't know, squared. And I need to square that as well, forgot that square there. Plus EG2, which is going to be M, 9.8 times a height of 3.05. Okay, so now what do we have in each equation that we can get rid of? Well, it's the mass, and that may be what you're looking at initially, thinking we don't have enough information, but since we have mass in every equation, we can get rid of it. So we can get rid of that, and that. We're just going to divide it all out. And then we're going to simplify our numbers. So 1/2 times 7.2 squared equals 25.92 plus 9.8 times 2.21 equals 21.66. And that's going to equal, and on the right-hand side of the equation, we have 1/2 V squared plus 9.8 times 3.05, giving us 29.89. So now we're going to collect like terms, we're going to simplify. We're going to take the 25.92 plus the 21.66 on the left, and we're going to subtract it by the 29.89 from the right-hand side, because we're going to bring it to the left-hand side. So minus 29.89, and that's going to give us the number 17.69, and that equals 1/2 V squared. V is going to be equal to the square root of 2 times 17.69, and that equals to 5.9 meters per second. And now there's no direction again because we're talking about energy. So what does this mean? Well, this means that as the basketball goes through the hoop, it's going to be traveling at 5.9 meters per second. And this makes sense. We had a speed of 7.2 meters per second. As it gained height, it would have lost speed. The energy from the speed went into the height, so our speed went down from 7.2 to 5.9. Other forms of energy. In the last example, we simplified things greatly by assuming that 100% of the energy was transferred between EK and EG. In reality, though, a great deal of that energy can be lost as other forms, such as sound, heat, thermal, etc., usually through friction. Energy is never converted from one form to another 100% efficiently. It just isn't. Energy is lost in more than one way. So for an example, light bulbs can only convert a portion of their energy to light. The rest is lost as heat. This is why light bulbs, especially incandescent ones, get really, really hot. If you're ever going to change a light bulb, make sure you turn the power off and wait at least 10 or 15 minutes before changing that bulb, because it's going to be really, really hot. Energy efficiency. Energy efficiency can be calculated as follows. Efficiency is going to equal to the useful energy output, so the output, divided by the energy input, times 100%. Keep in mind that work done is energy input. So whenever you're faced with a question that you don't really know what the input or the output is, keep in mind that the work done, the work inputted into the system, is the energy input. Different energy sources used to produce electricity, so fossil fuels, wind, etc., have different efficiencies based on the above equation. So what I want you to do is I want you to pause the video and then rank these from least to most efficient. Then I want you to watch this video to get the results. Once you have the results, compare your answers and see how well you did. Check your understanding. A family uses several planks to slide a 350 kilogram piano onto the back of a pickup truck. The box in the back of the pickup truck is 81 centimeters above the ground and the planks are 3 meters long. An average force of magnitude 1500 newtons is required to slide the piano up the planks. Determine the work done in loading the piano, calculate the efficiency of the planks as a simple machine to load the piano, and then determine where the rest of the energy went. So let's draw this out first of all. So we have our truck. So I'm just going to draw our truck right here. And we have our planks, which are going to load our piano onto our truck. I'm just going to draw a little dotted line to represent the ground here. Now we're told that the truck bed is 81 centimeters above the ground, so we're going to say 0.81 meters, and that the planks themselves are 3 meters long. The piano, the thing they're pushing up, is 350 kilograms, and a force of 1500 newtons is used to push it up the ramp. So determine the work done in loading the piano. Well, work, in this case, is going to equal to force times distance. Force is 1500 newtons, and it's sliding the piano up the ramp 3 meters. So 1500 times 3 is 4500 joules. B. Calculate the efficiency of the planks as a simple machine to load the piano, keeping in mind that work done is energy in. So efficiency is going to equal to output divided by input times 100%. So what's the input in this case? And what is the output in this case? Well, the input we just figured out was 4,500. We know it's going to multiply by 100%. But what is the output? That's going to be the question. Well, we can figure out the output by how much energy the actual piano has once it's on the truck bed. So how much energy does it have at this point? Well, it only has potential energy because it's not moving. So what is the energy here? Well, the only way we can figure out energy at the top is by saying it's equal to Eg, which is equal to mgh. In this case here, the m is going to be the mass, which is 350. G is 9.8, and the height is 0.81. 350 times 9.8 times 0.81 divided by 4,500 times 100% is equal to 62%. So in this case, the planks are efficient by 62%. C. Where does the rest of the energy go? Well, it's typically going to go to things like sound, as the piano is being pushed up the planks, thermal energy, as the piano is sliding up the planks. You're going to have that friction, that rubbing between the piano and the planks, and you're going to get a lot of heat being generated. So those are the two main places that the energy is going to go. And you can take it a step further. You can say how much energy is lost. Well, that's going to be the energy input, so the 4,500, minus the energy output, which is going to be the 350 times 9.8 times 0.81. And that equals to 1,722 joules. So you can say that 1,722 joules is lost to thermal and sound energy. Now here's a really interesting application. So whether you're talking hockey sticks, baseball bats, or pole vaulting poles, aluminum or composite materials are more efficient than the wooden variety. And you can see that different players use different kinds of sticks depending on their sport. As we get more advanced, as you progress in time, you see a transition between things like wooden and composite materials. You also see a price increase as well. Wooden materials lose more energy due to the amount of friction when they twist or bend compared to their hollow composite cousins. So why is this? As material twists and turns, the material that makes it up rubs against itself. So if you think about a baseball bat, it's going to be a solid structure. So you can have all the atoms within that solid structure rubbing against each other as it twists and turns. Right? As we twist it, as we sort of bend it in a little bit when the ball hits it, all the materials are pushing up against each other. But if you have a hollow or composite material and you twist it and turn it and push it in and stuff like that, when you hit a ball or make contact with an object, there's nothing for the outside atoms to push against. So they're just going to bend in, they're going to distort a little bit, but they're not going to be rubbing against all the atoms inside. So you're going to get a lot less friction, a lot less energy lost as thermal energy. So as it does, as these atoms rub against each other, thermal energy is produced, reducing the amount of energy available to the system. If you're going to use a pole vaulting example, for instance, you want to store as much energy in that pole as possible because all the energy is going to be transferred to you to get you higher up into the air. But if you lose a lot of energy, then your resulting height is going to be less. Same thing with a hockey stick. If you take a slap shot, typically what happens is that the stick bends. As the stick bends, it's going to store energy. So a normal stick would look something like this. when you're taking a slap shot, your stick's going to bend sort of in the middle. It's going to kind of go like that as an exaggeration. But then when it goes back to straight, when you make contact with the puck, all that energy is released into the puck, making the puck go forward with a certain velocity. If less energy is available, there'll be less energy delivered to the puck and less velocity of that puck as it leaves your stick. And that concludes our lesson on the law of conservation of energy and efficiency.